but when inert iron cores of stars having mass uh, having mass equals to a greater than 10 times that of the sun collapse, then it forms an extremely dense neutron star or black hole. Means in a very small region there will be very high density material. So that's why here we are saying we are saying that when we have the in the same radius we have the in the same radius we have the density 10 times density of the sun, then it becomes the black hole or compact stars. Okay, so these are some non-compact stars which are discovered by many researchers. Okay, so here we can see these are in these stars. So there we have this some range of these stars having the mass within the range which is shown in the table, and the radius which is also given in the table. So here we saw first, for example, suppose we have Hercules X1. So this star having the mass 0.85 to plus minus 0.15. It means we can take plus minus of this range. So 0.85 solar mass mass. So with the radius 8.1 plus minus 0.41. Similarly, we have other stars, those having the mass within these ranges and the radius. But in few researchers just they have fixed the mass, means because this is the because these radius are not fixed, because these are expected radius. So but some researchers thinks that mass are okay, but radius maybe varies. So still this is the topic of the research. What means what must be the radius of these stars? So according but right now we can compare our results, or we can our model. We have many models. Those are capable to represent these compact stars with these mass and radius. So now what is the white dwarf and black dwarf stars? So this is mainly consists of degenerated matter, typically carbon and oxygen, nuclei in a sea of degenerated electrons. White dwarfs are formed from the core of main sequences star, and therefore they are very hot initially when they are formed. As they cool, they will get dimmer and redden until they eventually become dark and transform into the black dwarfs. However, our universe has not aged enough for any black dwarfs to exist yet. Still, we are unable to find any black dwarfs. So white dwarfs are stable because there is a balance between the inwards pull of gravity and the degeneracy pressure of the stars electrons. After the degenerate stars mass grows sufficiently, that is when its radius shrinks to only a few thousands kilometer, the mass will be approach the Chandrasekhar limit. So in Chandrasekhar limit says that if mass of any star which is less than or equal to 1.4 solar mass, and those stars categorized as the white dwarf stars. Now, in neutron stars, if the if the white dwarf mass increases above the Chandrasekhar limit, it means when we have the white dwarf stars, those having the mass more than 1.4 solar mass, then the electron degeneracy pressure fails due to electron capture, and the star collapses into a neutron star. Means if we have when any stars having having the mass more than 1.4 solar masses, then we can say that that is the neutron stars. So for this, again for this, we have an equilibrium is possible after the star shrinks by 3 order of magnitude to each a radius between 10 to 20 kilometer. This is a neutron star. It means when any stars having the mass more than 1.4 solar masses and radius which is lie between 10 to 20 kilometers. So these stars categorized as the neutron stars. So and when magnetic poles of these rapidly rotating stars are aligned with the Earth, a pulse of radiations can be detected in each revolution. Such neutron stars are called pulsars. Now black holes. So if the mass of stellar remnant is high enough, the neutron degeneracy pressure will be insufficiently to prevent collapse below the Schwarzschild radius. As a consequence, the stellar remnant become a black hole with the accumulation of more mass. Means black hole means when that having the very high density materials or very heavily mass in a very few region, then these are the black hole and they will be gravitational force very will be high. So once the star's pressure is not sufficient enough to counterbalance gravity, a catastrophic implosion occurs within a fraction of milliseconds. The escape velocity at the surface quickly reaches the velocity of light. At that point, a black hole gets formed as no energy or matter can escape. The mass at which this occurs is known as with certain, but it is currently estimated at between 2 to 3 solar mass. And then now we have the quark stars. So if neutrons are squeezed sufficiently at a very high temperature, they will decompose into their component quark, forming a quark matter. Means just we have if any neutron star which having the very high temperature, then they become the quark matter, and they will shrink the star further and make it denser, and it is possible that the star may stabilize itself and survive in this state indefinitely as long as no more mass is added further. So it will to an extent become a very large nucleon A star. In this hypothetical state is known as a quark star, or more specifically a strange star. Means we can say that quark star, or we can say that strange star. And here we have some in this table. I have shown some models which are discovered by some authors. In 2015, which is 2015, they have a discovery model, and that model was capable to represent the wide dwarf stars as well as strange stars. And later on, 2018, some authors established some model, and those models are also capable to strange star and neutron stars. So here we have in that table we have some models. They are capable to represent wide dwarf stars, either strange stars or neutron stars, or either all the stars. So like here in this we can see that the first one capable to represent wide dwarf and strange quark stars, and third one that is discovered by in 2019, which is capable to strange star as well as neutron stars. So these are some few established models, mathematical models are capable to represent the compact stars, and these compact stars are categorized in these forms. All these are the compact stars, but we categorize these stars as a wide dwarf, strange stars, or neutron stars. Here we have some examples. Remaining this, apart from these models, also we have many models. So here I have shown only few models. Those are capable to these stars. And after this, after knowing about the theories of the compact stars, so we to establish the mathematical models, we need to know about the governing equations. Means how we can represent how these compact stars will be represented in mathematical forms. So to representing these forms, so first, we have to know about the governing equations, and these governing equations are known as field equation as well as are known as the Einstein field equations. So basically these are the Einstein field equations in the general theory of relativity. So these equations established a relation between the geometry of space-time and the distribution of matter within it. It is a compiling field for both mathematicians and physicists to discover new analytical solutions for these equations. Means ultimately, once we have the governing Einstein field equations, so ultimately we have to obtain the analytical solutions of the Einstein field equation, or we have to obtain the numerical solutions of the Einstein field equation. So in these two approach, we can find the solution of the Einstein field equations, and then after getting these solutions, we will utilize these solutions to establish the models to represent the compact stars. So for modeling, some simplifying assumptions are taken. We have to take on these assumptions that compact stars are assumed to be spherical and symmetrical. Means first we have to assume that compact stars are formed in the sphere. And then we have all physical quantities depends only on radical coordinate, that is R. Rotations and outside gravitational influences are generally ignored, because we have no effect. We have no discuss the effect these rotations and outside gravitational influences on these models. And it is considered that initial composition is uniform, that is no initial dependence on composition on radius, and gravity is Newtonian, and stars change slowly with the time. So after taking these assumptions, so we have considered a metric, that is spherical symmetric metric. So here we have that is the interior space-time, which is described by the following spherical symmetric matrix line element, which is simultaneously co-moving. And here we have d square equal to e raised power nu of r dt square minus e raised power minus lambda dt square minus r square dt d theta square plus sin square theta d phi square. So in this one we have the some spherical coordinates, and we have taken the time that is t. So as we know that any metric we use to represent the distance between 2 points or 2 objects. Okay, so in the first term, first we have the dt, that is the time. So this must also represent the distance, because all the other three components representing the distance. In other three components we have the space coordinate, that is r, theta, and phi. But in the first coordinate we have the only time coordinate. But there we have also c square, that is c square to dt square, and c that velocity of light, and dt that is the time. So ultimately, first component also representing the distance. And in this metric, that is the equation 1, nu of r and lambda of r, these are known as the metric potential, and these are the arbitrary functions of the radial coordinate r. And this metric describe describe the interior of the static and spherically symmetric stellar system. And in this metric, we have taken the signature of the space-time, that is plus minus minus minus. Because here we have the four. This is the metric in 4 dimensions, that is t, r, theta, and phi. So first component must be with the positive sign, and other three components must be with the negative signs. Some authors taken the same spherical symmetric metric with minus, plus, plus, plus. Okay, and both signatures are applicable, except applicable. So now after this, we have Einstein field equation, that is the equation number 2. So Rij minus half R delta Ij Gij. So Rij is the Ricci contracted tensor, and R is the Ricci constant, and delta Ij is the mixed tensor. So where Gij is the combination of Tij and Eij. So where Tij is the energy momentum tensor and Eij is the electromagnetic field tensors. So here we can see, so here we have the energy momentum tensor, which is given by the equation number 3. So that is Tij. So Tij basic, so it is a tensor. So it is a tensor of order 2, and it is a tensor of it is a mixed tensor, because one index is contavariant and one index is covariant, so that's why it is mixed tensor. And energy most in some books we can also see Tij as the contavariant or as a covariant, or we can take also as a mixed tensor. So all are acceptable. So here rho is the density, will be the, obviously it will be the matter, and pt is the pt represent the tangential pressure, and pr is the radial pressure. So these are the VII, that is xi, that is equal to 1, and VI xi must be this the product of inner product must be equal to 0. So VI, so the vector VI is the fluid for velocity, and xi is used as the space-like vector. Xi, not x, that is the xi. It is used for the space-like vector in the radial direction, which is orthogonal to VI. And electromagnetic magnetic field tensor, that is Eij, which is given by 1.4 pi, that is minus Fim Fjm. So Fim and Fjm, these are the electromagnetic tensors, and these are also Fij is also antisymmetric tensor. That is antisymmetric means that is if Fij equal to minus Fji, that is antisymmetric. And where Fij is defined as del Ij over del xi minus del Ai over del xj. So which is that must satisfy the Maxwell equation, and that is given that Fik comma j plus Fkj comma I plus Fij comma k. So where Fik comma j basically represent the derivative of tensor. If some of these quantities must be equal to 0, and square root of minus g, that is Fik comma k equal to 4 pi ji. So here Aj is the potential and Ji is the electromagnetic current vector defined as Ji, and that is equal to sigma over square root G44, and dxi over dx4 equal to sigma nu I. So where sigma is defined as the e raised power nu by 2 J0 represent the charge density, and G is the determinant of the metric potential or metric tensor. So here Gij is the metric tensor. So here in this metric, in this one, in the equation number 1, we have taken G11, G22, G33, G44. So in this one, G11 is a coefficient of dr square, G22 means coefficient of d theta square, and G33 is coefficient of d phi square, and G44 is the coefficient of dt square. Or in general form, we can represent the ds square as the metric tensor, that is Gij into dxi dxj, and when we take here I varies from 1 to n, j varies from 1 to n. But in these models, we have taken I and j from 1 to n. And J naught is the only non-vanishing component of the electromagnetic current Jij for the static spherically symmetric stellar system. And the total charge of the model or within the sphere of the radius, which is given by Q of R, which is represented by Q of R, and that is equal to R square into E of R, and that will be equal to 4 pi integration 0 to R J naught R square e power nu plus lambda by 2 dr square. So by this formula we can get the total charge of the within the sphere of the radius, means just we can get the total charge within the star, and where ER is the intensity of the electric field. And because these are some basics of the governing equations, so here Rij is the covariant curvature tensor, which is given by this equation number 6, and gamma Aij, these are the Christopher symbols, those are well defined, and first one is the Christopher symbols of the first kind, that is gamma Aij, and second one we have gamma Ij comma A, that is the second kind of Christopher symbols, and we define R equal to Gi into Rij just when we take the inner multiplication of two tensors Gij, Rij. So here we can see that upper indices and lower indices of the tensors are same. So when we multiply these type tensors, then rank of the obtained tensors or order of the obtained tensors will be reduced by 2. Okay, so in the equation number 7, two indices are same. It means order will be reduced by 4 order. So it means ultimately we will get a scalar, and that is we are representing by R, and that R known as the Ricci scalar. So after putting these Rij and these Eij and then Tij in the field equations, in these field equations, that Einstein field equations turn into the 3 equations. That is, we have equation 8, 9, and 10, and these equations are known as Einstein-Maxwell field equations. Because in the Einstein-Maxwell field equation, there we have the energy momentum tensor as well as electromagnetic magnetic field tensors. If we remove the charge from these equations, then just we have the Einstein. Then we can say that is the Einstein field equations only. But if we will consider the charges, the charge or electromagnetic tensors with the material, then these equations are known as Einstein-Maxwell's field equations. So in these equations, lambda, nu, rho, PR, PT, and Q, these are unknown quantities. So to obtain the analytical solutions of these equations, because in these equations here we have 6 unknowns and 3 equations. So it means we have to take any 3 components or 3 variables we have to assume, and other 3 we can find. So for that, so just after obtaining these three equations 8, 9, and 10, so when we take the differences of the equations 10 and 9, that is, so we obtain that is delta, and that is kappa pt minus pr, and that will come equal to this. So this delta is known as the anisotropic factor, and kappa is it is a constant, and that is equal to 8 pi g over c square. So where g is the gravitational constant and c is the velocity of light. So here we can see that delta is the difference of pt and pr, and this one is known as the anisotropic factor. So we can so now we can categorize these models in 2 types. One type is isotropic, another type is anisotropic models. In the isotropic models, radial pressures and tangential pressures will be equal. If these pressures are equal, it means their anisotropy will be 0. Okay, and if radial pressures and tangential pressures are not equal, then there will be some anisotropy that can be negative and that can be positive. So according to the negative anisotropy and positive anisotropy, we can categorize the forces as a repulsive or attractive. So the forces due to the anisotropy nature is represented by this del by R, and these forces of the stellar model is repulsive if Pt minus Pr is greater than 0. It means if delta is positive, then the forces of the stellar model will be repulsive, and if Pt minus Pr that is negative, so then these forces will be attractive. So these are some basic things of the governing equations to establish the model for to obtain the or to represent the compact stars. So after that, we have some stable criteria of the models. Means suppose we obtain some model, then how we can say that models are stable or not, models are physically acceptable or not. So there we have some physical conditions, and these conditions must be satisfied by the model, and if these conditions are satisfying, then we can say that models are physically acceptable or models are well behaved in nature. So first condition is that the internal metric and the external metric must be continuous over the surfaces. So internal metrics, that is the equation number 1 we have considered, and we we match these metrics with one known metric. Then we can take regional non-Western metric, as well as we can take Schwarzschild metric. Okay, so we equate the coefficients at r equal to r, and in the regular conditions, that is solution must be free from the singularities. It means the solution must not have the singularity. That is, for r, when r lies between 0 to r, the metric functions and the charge and the density and pressure must be non-negative. All means all these functions having the positive values, and they are well defined within the region that is r equal to 0 to capital R, and all these things must be positive. Okay, some authors consider also negative pressure, because pressure can be negative also, but still those models are available. All have considered only positive pressures, so that's why we are also considering the pressure must be only positive, density must be positive. And then third one is that the charge function, that is Q of R, that must be monotonically increasing function towards the surface. Means when we increase the radius, then value of the charge will be increased. And similarly, we can say that and density and pressure are the monotonically decreasing functions toward the surface. That is, when we increase the radius, then the value of the density and pressure will be decreased. So maximum pressure and density lies at the center of the sphere. These are some physical things. These are some conditions, and then the pressure and density must be maximum, must be positive, and it must be monotonically decreasing with its maximum value at the center. And radial pressure must be 0 at the boundary. We are assuming these conditions. At r equal to capital R, radial pressure must be 0. That is PR. That must be 0. And PT, the tangential pressure, and that can be non-zero. Still, PT is accepted if PT is non-zero at the surface. But again, this is again some researchers say that this must be also 0, and some authors, some researchers get tangential pressure also 0, but most of time again it is coming non-zero. And one more, we have the casualty conditions, and this condition is say that velocity of the means the magnitude of the speed of the sound must be less than the speed of the light. Once we have the density of any model, means of any star, so obviously that is rho, and that will be the expression in terms of r. And similarly, we will get the PR as the expression of the function of r, and similarly we can get PT. Okay, so velocity of these models defining by the square root of dp r over d rho and dpt over d rho. So we have this one. We have these equations, equation 8, 9, and 10. So to obtain the velocity of sound or velocity of the velocity within the star, velocity of the sound within the star, that will be given by that square root of dp r over d rho. So here we can see that density always will dominate the pressure. If density will dominate the pressure, so we will get square root of dpr over c square d rho. So c is the velocity of light. So at present we have no any material though that having the velocity more than the light. So that's why because density c square is the denominator. So obviously this quantity must be less than the 1 physically. Similarly, we can find the velocity with respect to the tangential pressure also, that is square root of dpt over c square d rho. So we have condition, that is the speed of sound should be a monotonic decreasing function toward the surface. Means velocity of sound will be maximum at the center of the star within the star, and it will be minimum at the surface of the star. So value obviously when we get the radial velocity, that is Vr, that is equal to square root of dpr over dt d rho. So pr is 0 at the surface. So at the surface, radial velocity will be 0. And both the velocities, that is Vr and Vt, must be monotonic decreasing functions toward the surface. And gravitational redshift as well as surface redshift should be positive and finite, and gravitational redshift should be monotonically decreasing in the nature with the increasing radius, whereas surface redshift should increase with the radius, and meet the value of the gravitational redshift at the surfaces. And then we have some energy conditions. So energy conditions, some conditions have been imposed on the linear relationship of energy density and pressure of anisotropic compact stars, which are collectively known as energy conditions. The solutions are required to fulfill all the energy conditions. So we have some conditions like means sum of the density, radial pressure, and tangential pressures must be greater than or equal to 0. So obviously all quantities are 0, or all quantities are greater than 0. So some of them will be greater than 0. And similarly, we can say that rho plus PR plus PT will be greater than 0. And similarly, rho plus 3PR plus 3PT will be greater than 0. And we have some strong energy dominant conditions and weak energy dominant conditions. So strong energy dominant conditions says that the density must dominate the pressure. That is, if rho minus PR is greater than 0, then we can say that density dominate the pressure weakly. So rho minus PR is greater than equal to 0 is the weak energy dominant conditions, and if rho minus 3PR is greater than equal to 0, then we can say that this one is recognized as the strong energy condition, strong dominant energy conditions. Because in the second one we have na, because density is greater than the three times of the pressure, so obviously that is energy dominating the pressures very strongly. So now these are some boundary conditions. So we match the given stoichiometric metric with the regional non-stoichiometric at R equal to capital R. So regional non-stoichiometric, which is given by, that is d square equal to 1 minus 2m over R plus q square over R square into dt square minus 1 minus 2m over R plus q square over R square whole raised to power minus 1 dr square minus R square d theta square plus sin square theta d phi square. So when we compare this metric, that is equation number 12, with the equation number 1 at small r equal to capital R, so we will get e raised power nu equal to 1 minus 2m over R plus q square over R square. That is capital R. So where m is the total gravitational mass of the model, which is defined by that xi of r plus zeta of r. So where zeta of r is defined by kappa by 2 integration 0 to r rho r square dr square, and xi of r is defined by kappa by 2 integration 0 to r small r into sigma q into e raised to lambda by 2 dr square. So q is the function of small r and lambda is also the function of r. So where xi of r is the mass and zeta of r is the mass equivalence to the electromagnetic energy of distribution. So when we compare the equation metric 12 with the equation 1 at small r equal to capital R, so we get e raised power nu of r equal to this, that is 1 minus 2m by capital R plus q square over r square, and e raised power minus lambda of r equal to 1 minus 2m by r plus q square over r square, and where q is the total charge within the star. That is small. If when we take small q equal to q of r, that small q of capital R, and that will be known as capital Q. So and the radial pressure must be vanished at R equal to capital R. So here we are just written P of R, that is the radial pressure, and that must be equal to 0 at the surface of the star. And now we up to this, just we have discussed about the well-behaved conditions of the model, and now these are the some conditions for the stability of the to check the model. So first one, we have the Hira cracking condition or average criteria. So in this one, that is del Vs equal to V square St of R minus V square of SR of R, and the condition is potentially stable region is if dVs lie between -1 to 0. If value of del Vs is lie between -1 to 0, then a model will be stable. Or if we get del Vs is greater than 0 but less than 1, that is potentially unstable region. So if del Vs keep the same sign everywhere within a matter distribution, so no cracking will occur. And second, next we have the Harrison-Zeldovich-Nevikov criteria. Okay, this criteria says that must just we take the derivative of total mass with respect to the central density, and if it is greater than 0, then we can say that model is stable. So where m is the total mass, and rho c is the central density, or this is the central density of the star. Okay, so it means so mass must be increased with the increasing central density. Okay, it means if central density will increase, then mass must be increased. Then so mathematically we can say that del m over del pc, or we can say that dm over d rho c must be greater than 0. And after that, we have the some about the investigating criteria regarding the adiabatic index, and this model will be stable if value of the adiabatic index, that is gamma, and which is given by the formula rho, that is the density plus radial pressure divided by the radial pressure into velocity of sound, that is dp r over d rho, and that must be greater than equal to 4/3. And later on, this formula is modified by after some time by modified by this formula, that is 4 by this quantity, left hand side quantity must be greater than equal to 4/3 plus 19 by 19 m by 21 r. So here we have some models. So here we have some models. Those follow the these stability criteria. So MGRD model, which is established into M50 model, and this one satisfies the causality condition as well as Hira cracking criteria as well as Chandrasekhar adiabatic conditions, and that has ZN criteria and TOV conditions. So TOV condition, I think. So in the TOV conditions, that is the form that is known as the Tolman Open-Meyer-Volkov conditions, and this one, and so in this one we have the just we can say that the Fa plus Fg plus Fh. Fa means anisotropic forces, and Fg means gravitational forces, and Fh means hydrostatic forces. So if some of these all these pressures are equal to 0, then we can say that that is known as the Tolman Open-Meyer-Volkov conditions. And this first model, that is MGRD, is capable to satisfy all the criteria except HZN criteria. That is HZN means Harrison-Jadovich Novikov criteria. So here we have I have just shown few models in the table. Those are capable to satisfy these stable criteria. Now, so after discussing the governing equations and the well-behaved conditions and the stability criteria, so our next task is that to finding the exact solutions of the Einstein field equation. So to get the exact solutions of the Einstein field equation is a very difficult task. So because the Einstein field equation are very highly nonlinear equations. So most of time, most of time solving these two, we use the similarity transformation methods. Because ultimately these Einstein field equations turn into the partial differential equations or ordinary differential equations. So by using the similarity transformation method, we reduce the partial differential equation into the ordinary differential equations, and again ordinary differential equation will be highly nonlinear, and again we will apply the similarity transformation on that one, and in that one, so we reduce the order of the ordinary differential equations, and we will try to find, then after that we will try to find the solution of the Einstein field equation. So in another approach, we can find the solution of the Einstein field equations by assuming the spherically symmetric metric. So due to the robust nonlinearity of Einstein field equations and thus the shortage of comprehensive rules to get all solutions, it becomes difficult to locate any new exact solutions. And the very first exact solutions of Einstein field equations representing a bounded matter distribution was provided by Schwarzschild in 1916. And thousands of the exact solutions of the field equation describing an outsized number of stellar objects varying between perfect fluids, charged bodies, anisotropic matter, distributions, higher dimensional stars, etc. But most of them are very physically relevant within the relativistic structure of the compact stellar objects. So, as the field equations of stellar structure are coupled differential equations, which has more unknowns than number of equations. Means there will be more unknowns the number of the known equations. So for that we have to consider some. We have to assume some variables, or we have to assume taken some assumptions or conditions also. So supplementary equations, that is the equation of state or data, are needed to solve it numerically. So simple approximation or assumptions help us to obtain a solution of the stellar structures problem without resorting a computationally expensive full solutions of the coupled differential equation of stellar structures. So now finding the exact solutions. So to finding the exact solutions, we have the two approaches. So in the one approach, that is, so one is to consider that the stellar model are homologous, that is all physical variables in stellar interiors scale the same way with the independent variable measuring distance from the stellar center and the stellar mass and is used as the scaling factor. And second approach is to suppose that at some distance r from the stellar center, the pressure and density means we in the second approach we will consider some relations between pressure and density, and that is related by PR over R equal to P of rho, and that is basically that is not P of rho, that is F of rho, means that is the relation between radial pressure and density. So in the second approach we can assume these relations. So now in the first we will discuss about the first approach, that is when stellar model are assumed to be homologous and the fluids and its gravitation are described by 6 functions depending on the radius, that is lambda, nu, q, pr and pt. And rho also. There are no, yes, in this one so there are only 3 essential field equations. So the presence of 6 unknown functions and just 3 essential field equations allow us to specify any 3 fluid characteristics and solve for the remedy. Means just we can assume any 3 and we can get other 3 by assuming these 2. So we can classify solution according to these features. Means first we can assume that lambda mu q, or we can assume that density nu and q. That is the first approach. Second approach, suppose we can assume lambda delta q or density delta q. In third approach we can assume that nu, means just we can assume these functions accordingly, because we know the behavior of these, means lambda and nu must be positive and these must be increasing. So accordingly we can choose a function lambda as such that the function is monotonically increasing in the range, and similarly nu must be the increasing function and q is also the increasing function, that is monotonically increasing. So because we know the nature of these things, so accordingly we can assume the function. Okay, Now in third one we can assume nu del Q. In fourth one we can assume that radial pressure, tangential pressures and Q, or radial pressures delta Q or tangential pressure delta and Q. In fifth approach we can assume that lambda nu rho, and sixth approach we can assume that nu rho PR or rho nu PT and rho nu density. Rho means density, nu means metric potential, PR means radial pressure. So basically we classify the assumptions in following 6 manners. So by considering these 6 manners, so many models have been established. In few of them, some consider lambda, nu and q, some consider rho, nu, PR, and so on. Accordingly, we can find the other remaining unknowns. So for example, just see the third one. In third one, that is this model is established in 2019, and in this model we have considered e raised power minus lambda equal to k into 1 plus cr square divided by k plus cr square. So we assume this one, and that is the so this one is the Bugdal metric. E raised power lambda equal to k plus cr square k into 1 plus cr square divided by k plus cr square. That is known as the Bugdal metric, and we assume that e raised power nu equal to f square. So still f is a known quantity, and similarly we have other models also. They have considered the metric. Some consider the lambda, nu and delta. Some consider lambda, nu and q, and accordingly we can find the other things. Now, so in the second approach, just we can assume the equation of state. Means equation of state means that is a relation between pressure and density. So this relation is known as the equation of state. So now, to obtain the stellar model, we can assume the equation of state, that is which relates the pressure to the density of the star, that is P equal to P of rho, and solve the field equations to explore the rest of physical properties. And equation of state remain a key aspect in the study of compact objects. In work involving general relativity, equation of state have been used in setting gravitational potentials and also ensuring that physical viability is maintained. A fruitful and physically plausible approach to stellar modeling within the framework of classical general relativity is to adopt an equation of state a prior, and the equation of state intimately connect the matter variables, for example, the energy density and the pressure of the stellar fluids. Because by this equation of state, we can connect the energy density with the pressure of the stellar fluids. So now there we have there is still a debate over the structure of a star as to its composition in terms of nuclear matter or quark matter or hybrid mix of both distributions. So it is difficult to find a single equation of state for a matter distribution matching the stellar core to outer regions. So now still, so there is no well-known equation of state that describes the exact structure of a compact star due to lack of knowledge of the nuclear interaction beyond the density 10 raised to power 14 gram per centimeter square. So now here we have the some equation of states. Those have been adopted by the researchers. First one, we have the linear equation of state, that is PR equal to alpha rho minus beta. So here alpha and beta are the constant, PR is the radial pressure, and rho is the density. Second one is the MIT equation of state. So again, so this is the more general form of the linear equation of state. So, and that is equal to PR equal to rho minus 4B minus by 3. So, and third one we have the quadratic equation of state. So we generalize we have taken the generalization of the equation of state. First we have linear equation of state. MIT again, MIT is also linear equation of state, but it is the some specific form. We can say it is the generalized form of the linear equation of state. And then after that we have the quadratic equation of state. So it is more generalized. Then we have the CFL, that is color flavored equation of state. So these are the some equation of these are some equation of state. These are assumed. And then we have the polytropic equation of state. So in the quadratic equation of state, we have PR equal to lambda rho square plus beta rho minus gamma. So alpha, beta, gamma are the constants. And in the color favored equation of state, we have the alpha is the constant, beta is also constant, and gamma is also the constant. So again, it is the more generalization of the quadratic equation. Then we have the polytropic equation of state, that is PR equal to beta rho plus alpha rho 1 plus 1 by n. So n is known as the polytropic index, and after that we have the Chaplin equation of state. So this is the specific Chaplin equation of state is the specific form of the polytropic equation of state. Okay, and then we have the van der Waals equation of state, and that is we have PR equal to gamma rho minus 1 by 3 beta rho minus alpha rho square. So now, so first we have the linear equation of state. So the simplest linear equation of state, the fluid density and pressure via a linear relation. An interesting study of compact objects in classical general relativity. So that is used by the Weathertaker 1982. This is the relation. A linear relationship between energy density and isotopic pressure. So isotopic pressure means just we assume that radial pressures and tangential pressures are equal. And with the help of this equation of state model, in which quark interaction was described by inner quark potential originating from the glucose exchange and by a density dependent scalar potential which restores the serial symmetric and high densities. The equation of state, that is P equal to P of rho, can be well approximated by a linear function by linear functions in the energy density and the linear energy density and the pressure. And the linear equation of state are relevant in the modeling of static, spherically symmetric anisotropic quark matters. So for the linear equation, linear equation of state, that is relation between radial pressures and density, is assumed in the form that is PR. That is, we assume that PR equal to alpha rho minus beta, and many models have been established by using this equation of state. And many authors like Maharaj, Chesi, Aloma, then we have the Turknes and Sarma. There are many authors, Moria, and myself also. So we have established many models with the help of this equation of state. So now similarly, then after that we have the MIT equation of state, that is PR equal to rho minus 4B by 3. So two observational data indicate the possibility of existence of a compact stars composed of deconfined quark known as the strange stars. So Nowadays researchers had mentioned about the possible formation of the quark stars and hybrid stars where quark matters are present in the interior. The simplest equation of state that governs these quark matters is the MIT back model, where quark matters are considered as non-interacting Fermi gas bound inside a hard sphere of nucleons. So these equation of states describing quark matters, and these are also relatively softened and right, since we don't have observed free quarks in an attempts to describe the quark confinement, right, mechanism to phenomenological MIT bag model is proposed where one assumes that the quark confinement is due to a universal pressure known as the back pressure at the boundary of the region containing quarks. The MIT bag models, motivated by the work in quantum chromatography, centered on quark confinement and asymptotic freedom, is essentially a linear equation of state. That is, we have considered PR equal to rho minus 4b by 3, and where b is the back constant. So this equation of state, many authors again they use this equation of state, that is Dave et al. Used in 2018, and then Kaumudi Raj and Sharma also used this MIT bag model. Goswami, Maurya, myself also used these equation of state, and then we have the quadratic equation of state. That is the quadratic equation of state, that is lambda PR equal to lambda rho square plus beta rho minus gamma. So a simple generalization of the linear relation between the energy density and radial pressure is a quadratic equation of state. So it means by considering the quadratic equation of state, we can think about the model in complexity form, because in the linear, as we know that in generally things are not existing in linear form. Most relevant models are non-linear. So it is quadratic equation is more relevant to the nature. So in the quadratic equation of state is a simple generalization of the linear, that is the relation between energy density, and it permits a more general behavior in the matter distributions and greater complexity in the model. The reason for this increased complexity of the model is the nonlinearity of the radial pressure in terms of energy density. Linear equation of state, like the MIT bag models, equation of state can only model quark stars, whereas with quadratic equation of state we can model both quark and neutron stars. Hence, the solutions obtained using quadratic equation of state has more advantage in the modeling of the compact stars. That's why some researchers more generalize the equation of state in the quadratic form, and that is we have PR equal to alpha rho square plus beta rho minus gamma. And after that, we have the color flavored log equation of state. So that is, so in this equation, so we have considered the equation in this form, that is PR equal to alpha rho plus beta by square root of rho minus gamma. So where alpha, beta, and gamma are the constants. So color flavored looking is a phenomena that is normally expected to occur in ultra high density strange matter, a form of quark matter. So many authors adopted a CFL, that is color flavored logged equation of state in the form that is PR equal to alpha rho plus beta by square root of rho minus gamma, which is generalize the MIT back model and describe the internal structure of compact stars made of strange matter in the color favored log phase. So when beta equal to 0. So when we take beta equal to 0, so this become the linear equation of state. We just take the beta equal to 0, so we get alpha rho minus gamma, and that is the equivalent to the linear equation of state. And then after this, we have the polytropic equation of state. So in the polytropic equation of state, we have considered PR equal to beta rho plus alpha rho raised to power 1 plus 1 by n. Or in some book you can say you can take eta. So polytropes are very useful to study the internal structure of stars. They can be used to discuss various astronomical situations and description of compact objects. The polytropic model have gained much attention in recent times because of their elementary equation of state. So in this form, so basically this one is the this one is the combination of the linear equation of state and the polytropic equation of state. So polytropic, so P, that is the PR plus beta rho plus alpha rho raised to power 1 plus 1 by n. So linear part is beta P, and polytropic part is alpha rho raised to power 1 plus 1 by n. So where n is known as the polytropic index, which is defines intermediate cases between isothermic and adiabatic thermodynamics process, and beta is known as the polytropic constant. And then after that we have the Chaplingan gas equation. So this one is proposed regarding treating dark energy and dark matter. Basically, this equation is used to represent the dark energy or dark matter in different manifestations of a single entity, leads to the Chaplin gas model. In the Chaplin gas model, the equation of state derives from the string theory. And this Chaplin gas model is one of the predicting candidates used to explain the present accelerated expansion of the universe. And we have considered the Chaplin of equation of state in the form that is P equal to H rho minus K by rho raised to power alpha, where alpha, H, and K are the constant, where K must be positive and alpha can be 0 as well as positive. So many scientists recently many scientists are showing the great interest in the Chaplin gas equation of state to explain the accelerating phase of the present universe as well as to unify the dark energy and dark matter. As you know that Chaplin gas equation of state is the specific form of the polytropic equation of state. Just if we assume that n equal to minus 1 by 1 plus alpha, so polytropic equation of state will reduce into the Chaplin equation of state. And then after this we have the after this we have the van der Waal equation of state. So the van der Waal equation of state has fascinated researchers for a long time, largely because of its flexibility. Here we have some about this. The van der Waals equation of state has fascinated researchers for a long time, largely because of its flexibility. This equation of state was proposed by van der Waals in 1873, his PhD thesis, and for this he was awarded the Nobel Prize in Physics in 1910. The van der Waal models is useful to explain the universe with a minimal number of ingredients, and the van der Waals gas treats dark matter and dark energy as a single fluid. It was discovered that assuming dark energy is governed by a perfect fluid equation of state may systematically include wrong results and be misleading in inferring the nature of dark energy. So in this spirit, an alternative model was proposed without the presence of exotic fluids, using a more complicated equation of state that is known as the Vandermeer equation of state. So after this, we can after this when we assume that space time is assumed to be conformal motion, so we can also establish some model. That is, suppose the existence of conformal motion are flat, motions are flat, or in particular provides an additional relation between both the metric potentials, or just this again reduce the original problem into the systematic system of 4 equations for 6 unknowns, and one can be obtained by the solutions by assuming two of the fluids characteristics as known on or imposing additional constraints in field equations. The complicated natures of the field equations allow the imposition of supplementary constraints like infinite Siemens point transforming, which leads to conformal motions. These are usually imposed on the system of field equations to make them easily integrable. The possibility of finding physically acceptable solutions with the conditions of conformal motions is probed into the depends crucially on the form of the conformal killing vectors field, that is Xi, and to obtain the nature relationship between matter and the geometry through the gravitational field equations. Inheritance symmetry can be used, and this symmetry known as the inheritance symmetry is known as the symmetry under conformal killing vectors, which is given by Lj Gik equal to psi Gik, where Lj is the Lie derivative of the metric tensor, which describes the interior gravitational field of a compact star with respect to the vectors field Xi, and psi is the conformal factor. And if it is considered that the vector Xi generate the conformal symmetry, and the metric G is conformally mapped onto the itself along Xi. If psi is 0, then equation 14 gives the killing vector. Also, in this case, underlying space-time is asymptotically flat, which is further implies that the wild tensors will also vanish. Means if you take psi is 0, so it will asymptotically space-time will be represent if flat is asymptotically flat, and the existence of conformal killing vectors implies a relationship relating the gravitation potential as follows. That is, we have this relation between nu and lambda. Here S is the constant, which is 0 for conformal. If S is 0, so then we can say that it is conformally flat space-time. Imposing these relations provide a systematic methods of generating solutions of the system of the field equations. So many authors have been used these approach. After that, we have one approach, that is, suppose we consider that space-time is considered to be of embedding class 1. So how first we will that how we will identify the embedding class. So suppose we have some metric with some dimension, and we reduce that metric into the flat space time. We need some more dimensionals. So differences. So these required dimensions will represent the embedding class of that. So for that, the embedding problem is one of the interesting problem of geometrically significant space-time. This was first addressed by Siklai on 1871, and on 1948, Karmakar derived the conditions for embedding for dimensional space-time metric in five-dimensional Euclidean space, and classified these space-time as class 1. So space-time of embedding class 1 is spherically case of the more general class M. So an n-dimensional Riemann space is called of embedding class M if M plus N is the lower dimension of the flat space. Okay, so here we can see that we reduce the n-dimensional Riemannian space into the flat space into the n plus n-dimensional flat space. So difference of these dimensions will represent the abelian class. So difference. So here to understand these things, so difference is m. So here we can see that will be the abelian class m. So so the resulting mathematical models has proved to be extremely useful in the study of the compact stellar objects. To solve the system of field equations, one can be employ the method use the Karmaka conditions, where the obtained solutions are classified as class 1 space-time. In this method, the Riemannian curvature tensors R, alpha, beta, mu, nu satisfy a particular equation that finally links the two metric potential e raised power nu and e raised power lambda in a single equation. And this Karmaka conditions, which is given by the equation number 16, that is R100 equal to R233 minus R1212 R3030 equal to R1220. So here R2323 must be non-zero, and these are when we put the value of R, these Riemannian curvature tensors in the equation number 16. So equation 16 reduced to the equation number 17. So that is the second order linear second order differential equation for nu. So to solving the 17, so Karmaka condition reduced to e raised power nu by 2 equal to this, that is a plus b integration square root of e raised power lambda of r minus 1 dr. So where a and b are the constant of integrations, and using the Karmaka condition, the expressions for anisotropy factor can be obtained by like this, that is del of r. So now, similarly, we can also study the anisotropic compact star in higher dimensions. The geometry. So the geometry of the space-time is regarded as the manifestation of gravity in the general theory of relativity. Therefore, it is reasonable to seek a higher dimension approach and determine whether those additional dimensions can play any significant role in describing nature. There have been widely researched efforts over the past few decades to comprehend problems in cosmology and astrophysics within the context of higher dimensions. As a result of recent advances in superstring theory, the studies in higher dimensional space-time have taken on the new significance. So the current 4 dimensional. So basically, currently we are working on 4-dimensional space-time structures. Sorry, wait. The current 4-dimensional space-time structure is widely assumed to be a self-compactified form of a multi-dimensional manifold, and it is suggested that unification theories required extra spatial dimensions in order to be consistent with the realistic model. Due to the development of superstring and supergravity theories, the study of higher dimensional theories was revived in 1970s. So many interesting theories of particles couplings require more than 4 dimensions for more consistent formulation. Because before this, we have taken the 4 dimensions spaces or structures and we discuss. But to discuss these theories, so we require the more dimensions, and thus it becomes essential to generalize the results obtained in 4-dimensional general theory of relativity in the context of higher dimension, and to investigate the effect due to incorporating one or more than one extra space-time dimension into the theories. So in 90s, interest grew due to the possibility of solving the hierarchy problem and lowering the grand unifications scale in theories. So many researchers have discovered that generalizing relativity theory to higher dimensions results in some unexpected and novel solutions that differ from four-dimensional solutions. For example, some properties of higher dimensional black holes differ significantly from those of four-dimensional black hole, because higher dimensions allows for a much richer landscapes of black hole solutions that don't have in dimensional counterparts. So there we have some. So in higher dimensions have been predicted by various gravity theories. For instance, the dimensions predicted by bosonic string theory, superstring theory, and N theories are respectively 26, 10, and 11 dimensions. Astrophysicists and cosmologists have shown an interest in studying the effects of higher dimensions on relativistic models. Even though there is currently no experimental evidence for higher dimensions, the extension of general relativity to higher dimensions has become a hot topic in recent years. So higher dimensions theories have been emerged as an active area of research in astrophysics to understand nature and very high energy scales. So, in addition to new physics, the results obtained in usual four dimensions have been generalized in higher dimensions. So, in n dimensions, Einstein field equations is given by this like this: kappa Tij plus Eij equal to Rij minus half Gij R equal to Gij. So, where kappa is 8 pi Gn by C4. So where C is the velocity of light, and Gn, which is given by G into V n minus 4, and here Gn stands for gravitational constants in n dimension, and V n minus 4 is the volume of the extra spaces, and the metric which is describing the interior of a higher dimensional spherically symmetric static space-time which is given by the equation number 21. So here we have ds square equal to e raised power nu dt square minus e raised power lambda of r dr square minus r square d ohm square n minus 2. So where d ohm square n minus 2 which is given by d theta 1 square plus sin square theta 1 d theta 2 square plus sin square theta 1 sin square theta 2 d theta 3 square and so on. It will goes up to sin square theta 1 into sin square theta 2 up to sin square theta n minus 3 into d theta square n minus 2. And the energy momentum tensors is considered in higher dimensions, which is given by which is written like this, that is Tij equal to diagonally, that is minus rho plus q square by r4, comma p r minus q square by r4 minus pt plus q square r4, comma it is up to, just we can take this one up to n dimension, and similarly we can describe the we can split the Einstein field equation into these three equations, that is we have the 23, 24, 25, and these are, so in this one rho, p, r, p, t, q are these are the unknown quantity, and again lambda and nu also is unknown quantity, and these are the in higher dimensions. And similarly we can take the regional non-Newtonian metric in higher dimension, that is given by the equation number 26. So So here we have we have some conclusion regarding this talk. So basically we have two approaches to generate the anisotropic compact star model. That is, one is charge model and another is uncharged model. So charged model means there will be some terms q of r, means there will be some so really q of r will not be zero for those models thoroughly. So obviously, so because q of charge is directly proportional to the radius, so it means at the center charge will be zero. And in uncharged model, just we assume that q of r equal to 0. So it means for the anisotropic compact star models, we can get charged model as well as uncharged model. And similarly, we can obtain the isotropic models also. In the isotropic models, isotropic charge model, uncharged model. So again, there will be, if there is if that model containing q, and that is the function, and which is non-zero thoroughly the model, it means that will be isotropic charge model. And if q of r equal to 0, that will be isotropic uncharged model. Isotropic means radial pressure and tangential pressures will be zero, will be equal. That is isotropic. And isotropic compact star models are also known as the perfect fluid models or perfect super dense star models. So now one can consider that the components of the energy momentum tensors are mutually independent. All these components are mutually independent. So consecutively, the system of field equations is solved by the assuming any theory. So that is the first approach to obtain the exact solutions of the field equations. We assume any three unknowns and try to find other three unknowns. And for that we have discussed the criteria. Some authors assume that lambda, nu, delta. Some assume that lambda, nu, q. Some assume that pr, delta, qt, and so on. So accordingly, some assume any three, and other three finds. So in that manner, we can establish the anisotropic model as well as isotropic models by assuming these three. And alternatively, we can impose some additional constraints on the system of field equations, assuming an equation of states, space-time, admitting conformal motions, or higher dimensional space-time of embedding class 1 in particular. So it means, so in alternative approach, just we can assume that equation of state, that is linear equation of state, and then MIT bag model, and after that we have the quadratic equation of state. Then after that we have the color flavored log equation of state. Then we have the polytropic equation of state, and after that we have the Chaplin gas equation of state, and then after that we have the van der Waal equation of state. So by assuming any one of these equations, so we can also try to establish some anisotropic as well as some isotropic models. Okay, and these constraints establish relation between the fluid characteristics, and thus these parameters remain no more independent to each other. Generally, in the second approach, after imposing one constraint on the system, two more fluids characteristics should be taken as given one. Means basically in the so ultimately in the field equation we have 6 unknowns now. If we assume one relation or one constant, that is the equation of state, so it means ultimately we have the 4 equations, because three are field equations, and one is the imposing equation of state. So remaining 2 we can find. So that will be more easily in compared to previous this one. That is the second approach. And however, more than one constraint can be imposed in the single model. So these are some references. So first one is that in the first paper, that is which is published in the New Astronomy Reviews. So in this paper, we have discussed discussed the many approaches or many ways we can establish the anisotropy model by assuming the first approach, second approach, or by assuming the higher dimension, or we have also discussed the we can also find these things with the help of the modified gravity. Recently, many researchers are working on modified gravity also, because up to this just I have discussed about the general theory of relativity or Einstein gravity, but many researchers are just modifying the gravity, and accordingly they have modified the field equations, and accordingly they have find the tangential and radial pressures, and they represent the some compact stars. So in the modified gravity, just they assume that some the functions, that is f of r, r means r is the where r is the Ricci scalar, and some assume that f of rt. So where t is the stress energy tensor, stress energy. Some assume that f of g or like that. So these are some modified gravity. So by assuming these modified gravity, many authors discuss many anisotropic model with the help of the modified gravity, and also many models anisotropic model has been discussed by the brain world gravity. So in discuss to just you can study this first reference. So this is the review article, and there you can find in detail all the things.